I spent a total of 2 years working as a data analyst for the same company, and I discovered 4 different types of data problems that I'm going to share with you today in this video. This is me. After spending countless of hours watching YouTube videos and earning a certificate from a paid course, I was feeling ready to change the world. So one time, here's what I did. I was going to implement a dense neural network in order to predict customer behavior and future sales. I mean, come on, it's so cool. I learned how to do it and I just couldn't wait to try it out in the real world. But there's one problem. No one in the business was asking for it. While a model based on a neural network may become useful in the future, in reality, stakeholders in the business may have other priorities. Some people only want to know what's happening at a given moment and be able to keep track of business metrics. Others may want to know the relationships between 2 or more variables in the business, like products purchased versus the types of customers they deal with. And some other people may want to know what would happen if they release a new product or variety into the market. So making a prediction using a machine learning model that you learned in your bootcamp is just one type of problem. The other types of data problems are descriptive problems, correlational problems, experimental problems, and again, predictive problems. So we'll walk through each one of the types of problems and we can look at a few examples to really understand what they are. In your first week as a data analyst, you might be told to make a report periodically. If you have all the data available to you and if that's all you'll ever do for the rest of your life, well, that's great. Easy job, easy money. You might think that this is a trivial job, but to company leaders, this is crucial and you have to make sure to get the numbers right. But some questions cannot be answered precisely with one answer, unless your boss insists. For example, what's the potential business value of one sign-up? What is the typical churn rate? Okay, so now things are a little bit more interesting because you can now use statistical tools like mean, median, standard deviation, and maybe theorize some probability distribution to describe the data, which could look like a Gaussian distribution, i.e. the famous bell curve distribution, or it could be something else entirely. But the challenge of this type of problem isn't really technical, it's a social one. People who don't usually deal with data don't always understand how data analysts deal with uncertainty. The way we deal with uncertainty is to give a range of values wherein the true value may lie and that we're 95% sure of it. But if I must give one number, I would often give the average or the mean, and sometimes the median if the data is extremely skewed. In a simplified reporting, I don't typically report the standard deviation, but I keep that documented for someone else taking up my role in the future.
Here's Johnny!
The next type of data problem is the correlational one. This is where things get exciting because now we're able to see all the different angles to our data and add context to it. Stakeholders may want to know all the important variables that can affect sales and how much does each variable contribute to the final outcome. Let's say you're analyzing data for an e-commerce company, specifically looking at variables like marketing spend and website traffic against weekly sales figures. Visualizing this on a chart would actually help. Alright, we're seeing a lot of business in the last few weeks of the year, but let's focus our attention on marketing spend and website traffic since we can confirm that website traffic correlates well with sales. But what's going on here? Marketing spend has a moderately negative correlation with web traffic? Does this mean we should stop it entirely? Based on industry experience, ads generally tend to bring traffic. And spending more means getting your ads out there for longer to attract more traffic. So if ads generally work, maybe it doesn't work immediately in our case. There might be a 1-week lag. So what we can do is to shift the marketing spend column down so the effect of ads in week 40 is accounted for by the web traffic figure in week 41. Great, so now the 2 variables seem to line up more in the chart, but the correlation is still negative. We can tell that we must take into account an external factor, which is time or seasonality, because we can see that web traffic is positively correlated with time from week 40 onwards. What if we exclude week 49 onwards? What would happen to the correlation between marketing spend and traffic? Whoop, turns out paid advertising does influence web traffic, but up to a certain point. Past week 48, the effects of seasonality takes over by a huge margin. And as a bonus, we can also use linear regression to visually see the relationship between the two variables. So far, we've only been reacting to whatever happened in the past by looking at historical data. But sometimes an opportunity comes along in the form of A/B tests or even quasi-experiments. An A/B test is an experiment where you take randomized samples of your users or customers and divide them into two groups, the control group and the treatment group. The treatment group will be exposed to experimental variables, for example, a change in a website layout, terms of service, or pricing. Yep, as you can already tell, my examples are biased towards something that I'm familiar with, which is e-commerce. But A/B tests can also apply to other industries like healthcare, where the treatment group gets the test drug, while the control group typically gets the placebo. The results of A/B tests often have strong validity because you can isolate the effects of experimental variables due to randomized sampling and also environmental control. However, randomized sampling can be impractical or even unethical in some cases or industry. For example, in education, for the same classroom or cohort, it might be unethical to give only some students the experimental treatment, for example, given free access to resources and not to the rest. So in practice, a quasi-experiment might occur when one school from one part of a country gets the experimental treatment, but not another school from another part of the country. But in either case, you're given knowledge of which group is the control group and which group is the treatment group when you're analyzing the raw data. And then you can use statistical methods like significance testing to see if the treatment has any effect on the desired results that you want to see. Also, bonus points if you can identify confounding factors. In quasi-experiments, there are obviously many confounding factors that you can identify because you don't get to control a lot of the variables. But this is also true of A/B tests. Due to legal reasons, we're not allowed to experimentally sample users by demographics, socioeconomic factors, or even geopolitical factors in some places. And finally, the fourth type of problem in data science is the predictive problem, which gets disproportionate amount of attention and hype. While it's cool to be able to train a model and use it to predict the future, you have to stop and consider the overarching goal of this type of problem. You see, we want to estimate something given that we already know about some other things that can relate to it. Suddenly, this type of problem doesn't sound all that difficult or cutting edge. While machine learning algorithms can be useful in this scenario, they're not strictly necessary. This type of problem can be found in these questions. If a customer likes product A, which product will they also like? If a customer is over 50, how much money might they spend in the first year? If a person has an income of X dollars per month, how many kilometers would they travel in 1 year? And you know what? These types of questions can be answered without resorting to advanced machine learning algorithms. In fact, you can answer that with tools that most people can already understand, which are correlation analysis and linear regression. Okay, great. So does this mean that this type of problem is the same as the correlation problem? Well, not quite. The correlation type of problem looks at data that's already available. The predictive type does that and takes one extra step and tries to estimate for missing data. For example, if we have a relationship between age and average spend in dollars, you might come up with a linear model to describe the relationship using a line of best fit, and you can call it a day. But if we're interested in making interpolations or even extrapolations, we'd now have to use a different approach because this type of problem is now a predictive data problem. So how different can the approach be? Firstly, we have to randomly split the data into two sets, a training set and a testing set. Then we create a model that fits into the training data set. Then we use the testing set to see how well the model can perform on a data set that it has not seen before. Alright, so to recap, on your job as a data analyst, you will encounter at least one of these types of problems. You might be asked to come up with one answer, even though your data is quite nuanced and full of variation. You might be asked to find the relationships between two or more variables. You might be asked to evaluate an experiment and find out if there's any real impact from a variable that your company is testing. And finally, you might come across a problem where you need to predict something based on relationships between variables that are known. So this list isn't extensive, there could be more that I missed, but so far in my job as a data analyst, these types of problems are so common that I just like to group them into 4 little boxes. Alright, so if you enjoyed this video, please like it so that more people can see it. And if you want to see more videos like this, please subscribe, and I'll see you in the next one. Bye-bye.